Hello, I am Arnav Malawade from UC Irvine, and I'm presenting our paper titled SAGE, a split architecture methodology for efficient end-to-end autonomous vehicle control. Autonomous vehicles are expected to revolutionize transportation and road safety. However, driving safely is a challenging task. To meet this challenge, the computational complexity of AV software is increasing over time. Conventionally, these models are run entirely on the AV, but this requires powerful hardware platforms that consume kilowatts of power, which can reduce driving range significantly. To address this, recent works have proposed offloading some or all of the computation from the AV to the cloud. However, they cannot meet strict latency deadlines for AV control at current network speeds. To address these challenges, our goal is to design an offloading strategy that reduces AV energy consumption, is feasible at typical wireless network speeds, and does not require hardware or infrastructure changes. We propose a solution based on split architecture computing, where a deep learning model is split into two pieces, a head and a tail. Then we insert a bottleneck layer to serve as an optimal offloading point. At runtime, if network conditions are sufficient, computation can be efficiently offloaded to the cloud at the bottleneck to finish execution. We target end-to-end AV control, where an input is passed through a deep imitation learning model to generate a set of control outputs. To account for performance impacts from the bottleneck layer, we use head network distillation to train our bottleneck head model to mimic the behavior of the original head model. This results in a mean absolute error within 1% of the original model for all model variations tested. For our experiments, we converted well-known perception models into deep imitation learning models for AV control. We evaluated energy consumption and model latency on both the NVIDIA Jetson TX2 and the NVIDIA Drive PX2. With one 720p camera as input, we found that DenseNet and ResNet models can meet the latency deadline and save energy while offloading at typical 4G LTE and Wi-Fi speeds. We also found that SAGE was less effective on the smaller CarlaNet model, as it required more energy to offload than to execute locally. We found that SAGE reduces energy consumption by 47% compared to edge-only computation. We also evaluated SAGE with three 720p camera inputs. We used both 16-bit and 8-bit quantization at the bottleneck, which reduced transmission data size by over 96% without affecting model performance. We found that it's again feasible to offload DenseNet and ResNet models at typical 4G LTE data rates, and that offloading reduces energy usage by 55% compared to edge-only computation. Thank you.